All right, welcome back. So we are now moving into chapter 10. We're going to talk about things called sequences and series. Sequences and series. Uh, so we start by talking about these things called sequences. The definition might seem kind of a little strange here. All right, a sequence, the notation is braces A sub n, is an ordered list of numbers of the form A1, A2, A3, continuing on AN, and then on forever. All right, a sequence is a list of numbers that continues on forever towards infinity. Okay. Now, you've seen and dealt with sequences before. In fact, a lot of times you're asked to use sequences to notice and identify patterns. So here's an example of a sequence. 1, 2, 3, 4, 5. Of course, the implied idea here is that that's going to continue moving the same way as what's been described already. All right, so you've done things like this where you've been asked to compute the next term or the next few terms based on the pattern that's there. Okay, as a second example, 2, 4, 6, 8, 10, and so on. Or as another example, 1, 2, 4, 8, 16, 32, and so on. Okay, so those are just a couple of examples of some sequences. And my intention here is that these follow the pattern you would expect. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. 2, 4, 6, 8, 10, 12, 14, and so on. 1, 2, 4, 8, 16, 32, 64, 128, and so on. Right. But it actually turns out just having a list of the first few terms and no other information about your sequence, you can actually generate a sequence where the next number can be anything you want, technically. So those old questions from elementary school and stuff where you were looking for patterns, the reality is you can actually mathematically make that next thing be whatever you want and still come up with a formula for it that would match, let the first 5 things match what it is. So just just be aware of that idea that they're actually, you could write down anything you wanted and it would technically be correct. But we're going to be looking at the pattern as it's described, the most common pattern. So now, sequences can be defined in different ways. Sequences can be defined in different ways. The two ways that we're going to be most interested in, the two ways we're going to be investigating, is that a sequence can be defined using an explicit formula. So we use an explicit formula. Or the second way that we can define a sequence is by using what's called a recurrence relation. I'm using what's called a recurrence relation. I'm going to show you an example of each of those two ideas here as we start to introduce sequences. Of course, you can define sequences other ways, right? We could say, hey, I'm going to make my sequence be just the digits of pi. So the first number in my sequence is 1, the next number is 4, the next one is 1, the next one is 5, the next one is 9, the next one is 2, and so on and so on, out through all the digits of pi, right? Now, unfortunately, for something like that, we couldn't describe a formula to give us that, right? We don't have a formula that's going to tell us the nth digit of pi, right? So the only way to get the digits out of that sequence is by generating the next digit of pi, right, through some approximation method. But we could define our sequence like that, and so you can have sequences that don't have a describable pattern. And that's perfectly fine too. But we're going to be focusing on ones that can be dealt with either an explicit formula or a recurrence relation. So for example, consider the sequence that's defined by the formula a sub n, the nth term, is just equal to n squared. Okay, and so the first term in our sequence, again, is a1, and a2, a3, and so on. So using that formula, we could say that the sequence a sub n, as described by that formula, would start off a1 is 1 squared, a2 is 2 squared, a3 is 3 squared, a4 is 4 squared, a5 is 5 squared, and so on forever. Right, so that's a sequence that's defined by a formula in terms of the index, based on the position. Okay, so that's a sub n. The second way to describe it is by using a recurrence relation. So we would see something like this. A sub n is equal to n times a sub n minus 1. And with recurrence relation, we have to have a starting point. So this is true where a sub 1 is equal to 1. Okay, so using that formula, a sub 1 is 1, so a sub 2 would be n times a sub 1, which should be 2 times 1. So a sub 2 would be 2. And then we keep going. A sub 3 would be 3 times a sub 2 would be 6. A sub 4 would be 4 times 6 would be 24. A sub 5 would be 5 times 24, which should be 120. So the first few terms of our sequence here, generated by this recurrence relation, would be 1, 2, 6, 24, 120, and so on forever. So we can develop sequences either from a formula, where it's just like a function in a sense, or from a recurrence relation, where we have a starting point and then a formula for the successive terms after that. And that's where the next term is expressed in terms of either just the previous term, or it actually could be a combination of some of your previous terms. Okay. And then some recurrence relations can then also be transformed and expressed in terms of a formula. So you use the recurrence relation to try to generate a formula that you can use. So some recurrence relations can be done for. Okay, so this is kind of just an introduction here to sequences. We're going to move on now and look at sequences both in terms of a formula and also a recurrence relation, and I'll formalize the recurrence relation stuff idea a little bit more than rather than just doing an example. I'll kind of give some background, a little more information on that when we get to it here in just a little bit.